Hello friends, we start with our next topic. Till date under initial condition we have completed our two topic in which we have studied about RC and RL circuit under no excitation condition, and we have seen different type of concepts. Now we go for the analysis of RC circuit when some excitation is applied. Okay, so till date I think you have understand about RC and RL circuit conditions when there is no excitation applied in the circuit, and we have seen the behavior of RC and RL circuit. So now we start with our RC circuit and then we'll go for RL circuit. So we'll see RC circuit when excitation is applied. So till date or up to till video you have not subscribed, comment and like my channel, please do it. Once you subscribe it, it will be more easy for you to go through my all previous video. The link of my previous video is already mentioned in my description box. You can go through it and try to understand it. Okay, so we start with our next topic, that is known as analysis of RC circuit when some response or some excitation is given. Okay, so we'll see RC circuit analysis when some excitation is given. Or you can say under excitation condition. So to analyze such type of circuit, we will consider one circuit. Let it is an RC circuit. This is your R, this is your C. Okay, and now it is excited by, let some voltage source, that is a DC voltage source, and whose value is Vs. This is R and this is C. I am considering let some voltage V is appearing here, and so this is the circuit condition. Okay, this is the circuit condition. Here this Vs is basically VSUT. Very important thing. VSUT, it means it represents that the DC voltage is in the form of Vs, which is applied in the circuit, and it is basically VSUT. So a DC source of VSUT is applied here. Okay, since we are talking now about the RC circuit analysis when some excitation is applied, that means we have to consider this circuit with respect to the time. Okay, so this is your DC excitation R and C. This is the voltage which is appearing across V. Now what I will do, I will redraw this network once again, and if you try to understand it, this is basically this your Vs. For more understanding, what I will do, I will take one switch here. Okay, now again this is your C, this is switch, this is R, and again this is Vs. Okay, now before going for this RC analysis, one thing which you try to understand, you will find in analysis different type of switch conditions. This may be the condition, this may be the condition. Okay, so this condition represent that at t equal to 0 the switch is going to be closed. This is condition A, this is condition B. So always remember that this condition represent that at t equal to 0 this switch is going to be closed. Okay, and at this condition at t equal to 0, it represents that the switch is going to be opened. Okay, so these are the two different type of condition. This is the condition when switch is going to be closed. The very important thing, at t equal to 0, and similarly the switch is going to be opened at t equal to 0. So sometimes this is representing in this form and sometimes it is not mentioned here. So you always remember that whatever the condition of switch is given, it is always at t equal to 0. So either the switch is going to be opened or the switch is going to be closed. So these two conditions just keep in your mind. So from here, this switch condition represent that the switch is going to be closed at t equal to 0, and and a voltage which is appearing is known as the voltage is V. Again, this Vs is your VSUT. Basically, this is your voltage. Okay. So now you have to analyze this circuit when such voltage is applied across this RC circuit, and at t equal to 0 the switch is going to be closed. Now the very important concept which is coming here, I am saying that the capacitor is initially charged. This we have seen in our RC circuit analysis while we are not considering the this excitation voltage. So what is now different, because in that condition also we have seen that capacitor is initially charged, and here also we are seeing that capacitor is initially charged. So for the time being I will take that initial charge voltage across the capacitor is V0. That voltage is what? V0. So now here appear a very important condition which I am writing here as VC0 negative and VC0 positive is equal. Now the question comes to in your mind, what is VC0 negative and what is VC0 positive? Now question comes to your mind, what is VC0 negative and what is VC0 positive? Okay, you know that the current across the capacitor is C dV by dt. Yes, this is a current equation. What is the point here is, I said the initial voltage in my previous video when I was talking about, so I have just mentioned here as V0 as V0. Okay, and I call that this voltage is initial voltage. So now what is 0 negative and 0 positive instant? Actually it represents that when the switch is just closed, when this switch, okay, this is your switch, when this switch is just closed, that is at t equal to 0, so that means there exists an instant, if it is 0, so there exists an instant that is t equal to 0 plus, and there exists an instant that is t equal to 0 minus. Okay, but we are saying that whatever the voltage across the capacitor at t equal to 0 negative is always equal to the capacitor at t equal to 0 positive. Okay, so this is a very important condition in which it reflects that whenever you are going to solve any type of initial based problem, you have to consider this condition that whatever the voltage at t equal to 0 negative, that is VC0 negative, this VC represents the voltage across the capacitor, so VC0 negative is equal to VC0 positive. Okay, now your point is why it is equal, why not it is not equal to each other, why we are considering that VC0 negative and VC0 positive? See what happened, the instantaneous behavior across the capacitor will not changed. Okay, that means if this condition is not applicable, that means if you talk about this instant t as 0, this I will become, now if you see, if I taken t as 0, this I will become what? It is infinite. Okay, this I will become infinite. That means at t equal to 0, if infinite current flow across this capacitor, then this condition will not exist. Okay, and you can solve the network. But is it possible that the value of current goes infinite when t tending towards the 0? No, it is not possible, because it is just a theoretical concept. This is just a theory in which we used to understand that once t goes 0, definitely I goes infinite. But such type of condition never appears in the circuit, and since this type of condition never appears, the reason is that whatever the voltage at time t instant, that is at 0 negative, will remain equal to at 0 positive, and that's why whatever the initial voltage exists across the capacitor at time t equal to 0 negative is always equal to the voltage at t equal to 0 positive. Okay, so Vc 0 negative and Vc 0 positive are always equal. Okay, so from here one thing which is very clear, that in entire initial conditions problem, you always keep remember that since this condition is not possible, therefore the initial voltage across the capacitor at time instant 0 negative and 0 positive will become equal, and one can easily able to solve the situation or conditions of voltage current across the capacitor at time t equal to 0. Okay, so this is all about the initial condition. In our later course of problem solving sessions, we will more understand about these conditions and we will see how it is applicable while solving the problems. Okay, so from here we have finally understand that this voltage is V, initial voltage is V naught, that means Vc 0 negative is equal to Vc 0 positive, that is equal to V naught. Very important thing, this is your initial condition. This I am explaining here just to understand it. As of now it doesn't have any use right now here while solving the problem, but yes, we will see in our problem solving sessions. So from here at t equal to 0, this switch is closed, so this is your network, this is your network, this is R, this is C, and the voltage appearing here is V. So if I apply KCL here at this node, so this comes to be C dV upon dt, the current here, this current and this current I am considering, plus of V minus of Vs upon R, that is equal to 0. Yes. Okay, from here if you solve this equation, this comes to be dV upon V minus of Vs, that is equal to minus of 1 upon Rc, and here it comes to be dt. Very simple, simply will integrate it. Now again that limit comes to be 0 to t. As I mentioned earlier, limit is from 0 to t, that means we are talking about the initial value. So here the initial value is what, your V naught, and it goes to a solution that is Vt. Since we are finding out the solution for Vt, so your limit will become initial voltage to your final value, that is Vt, and here it is from 0 to t. Now if you integrate it, please integrate it, so that comes to be ln, that is V minus of Vs with limit of V naught to Vt. Okay, see this V is a function. Okay, so whatever the limit we will put here is the limit which we are going to put here. Okay, so just consider here, that is equal to minus 1 upon Rc t with limit 0 to t. Okay, now once we will solve it, so when you solve it, it comes to be, I am writing directly ln, that is Vt minus of Vs upon V naught minus of Vs. Okay, I have just solved it, and that comes to be minus 1 upon Rc, that is t. Very simple, you just put it down the limits and you have solved it. So that comes to be Vt minus of Vs upon V naught minus of Vs, that comes to be minus of e to the power minus t by Rc. Okay, it is e to the power minus t by Rc. I have just transferred it. So from here you can say that Vt minus of Vs is equal to V naught minus of Vs into e to the power minus t by Rc. Okay, and finally from here the value of Vt comes to be what? It is Vs plus of V naught minus of Vs e to the power minus t by Rc. So this is the voltage Vt. This is the voltage Vt across the capacitor. If I write it here, the value of Vt comes to be Vs plus of V naught minus of Vs into e to the power minus t by Rc. Okay, so this is your Vt, very important. So that means if I write this voltage in terms of the time function, so you can say that it is V naught when t was less than 0, or you can say that it is Vs plus V naught minus of Vs e to the power t by Rc for t greater than 0. Yes, this is the solution of voltage across the capacitor when switch is closed. So when t was less than 0, it is V naught, yes, the initial voltage. But when t was closed, so for t greater than 0, the solution comes to be Vs plus V naught minus Vs into e to the power minus t by Rc. Very important expression. Now we analyze this expression. So friends, we have find this solution, that is Vt is equal to V naught for t less than 0 and Vs plus V naught minus Vs e to the power minus t by tau for t greater than 0. This is for an RC circuit where tau is equal to your time constant, that is Rc. Now if we analyze this equation, please see, if I write once again Vt is equal to Vs plus V naught minus of Vs e to the power minus t by tau, this is our equation, which is very important because this basically is your solution. So here if you see this Vs and if you see this V naught is basically initial voltage. Yes, this is your initial voltage. And if you talk about Vs, this Vs, so this you can say it is your final voltage, or you can say it is an steady state voltage, or you can say it is an steady state voltage. That means once the capacitor will get discharged, okay, once the capacitor will get discharged, this voltage will remain in the circuit. So you can say it is a steady state voltage. We will see by diagram also. So should I write this equation in the form of V infinite plus of V0 minus of V infinite into e to the power minus t by tau. Yes. So this is now basically the solution, and you will find this equation everywhere, where V infinite represent your steady state value of voltage, V0 is your that is initial voltage, and it is e to the power minus t by tau. So finally you can say that your Vt is the voltage that is this is the value of your Vt across the capacitor, and based on this formula we will solve all our problems. So just keep in mind, this is the voltage Vt, which is also represented in this form. Okay, so this is just a symbolic notation. Now once again we will consider our this equation. So as I mentioned, for t less than 0 the voltage is V0, that is your initial voltage, but for t greater than 0 this is the voltage. Now if initial voltage will go 0, it means initially the capacitor is uncharged. You can say initially capacitor uncharged. If capacitor is uncharged, that means V0 goes 0. Under this condition the value of Vt comes to be what? It is 0 for t less than 0, or you can say it is Vs 1 minus e to the power minus t by tau for t greater than 0. So this is our solution for Vt, or you can say finally this is our solution. This is our solution. Okay, if I have to find the current across the capacitor, so from here I can write it as I equal to C dV by dt. Okay, so once you differentiate it, you will get a current here. Okay, so if you differentiate this comes to be C into, if I am differentiating this voltage, so what it is, this is a constant, so that comes to be Vs, and once you differentiate it, this comes to be tau, and it is e to the power minus t by tau. Okay, the value of tau is Rc. When you put the value of tau as Rc, so the current value I comes to be, that is C into Vs upon Rc e to the power minus t by tau, or you can say it comes to be Vs upon R e to the power minus t by tau in amperes. So this is the value of current across the capacitor, and similarly Vt is equal to 1 minus e to the power minus t by tau, that is Vs into 1 minus e to the power minus t by tau. So this is the voltage across the capacitor. So these two formulas are the important formulas, the current across the capacitor and the voltage across the capacitor. This is also in the form of IT. Okay, I have just not mentioned here, but you keep remember, this is also in the form of your time function. So this is IT and this is Vt. If you see, we will draw it also. If we draw Vt, so what is Vt? This is the level of your Vs, and 1 minus e to the power minus t by tau is the graph which is moving in this fashion. Okay, this is for Vt, this is your Vt. And similarly, if you draw It, this is what? It is Vs by R is the level here, and this is exponential decaying. Again, this is T, this is It. So you can see that the voltage Vt is in this form and the current It is in this form. Once the capacitor will get fully discharged and the steady state achieved, the current goes 0. The current goes 0, very important thing. We will see its application in our later course of numerical problems. Okay. So this is all about the capacitor, in which we have seen the voltage and the current. It is in the condition when initial voltage is 0. Okay, so this we have drawn for capacitor, that is RC circuit. Now finally friends, we have seen all the aspects in RC circuit. The last aspect, we will see the different type of behavior of solutions that we have to see here also. You will listen about few of the solution which I write here as natural response and forced response. This is our first point. Second is zero input response and zero state response. Third point is transient response and steady state response. And if you talk about mathematics, the another term comes to be CF plus PI, complementary function and your particular integral. So there are four different type of response you will see in your control system, also in networks, or in so many subjects you will find such type of responses. So we will little bit understand in networks, because sometimes such type of problems used to come in which they will ask you problem in the form of responses. So there you have to understand what is natural response, what is force, what is ZIR, what is ZSR, what is transient, what is steady state. Okay, so we will see one by one each. So first we will see the natural response and forced response. Okay, just try to understand what is natural response and what is a forced response. Okay, for this I am considering the equation of Vt, that is Vs plus of V0 minus of Vs e to the power minus t by tau, or as I mentioned just now, you can also write it as in the form of V0 minus of V infinite into e to the power minus t by tau. This equation we have seen just to understand RC circuits, but now this is our important equation, because you will see in all the problem solving sessions we will go through this equation. So this is important equation. Now for this equation, if I write it as Vt is equal to, for the time being I am considering this equation, I write it as V to the power V0 into e to the power minus t by tau plus of Vs 1 minus e to the power minus t by tau. So this is one type of response, this is another type of response. Now if you see, this response is because of this voltage V0 which was initially stored in the capacitor, and we have seen our RC circuit analysis without excitation. There I mentioned you this type of response is referred as natural response. This type of response is referred as natural response. Why natural? Because there is no external sources, and the circuit, whatever the nature of the circuit, it is only because of that initial voltage which is present across the capacitor. So that's why it is called as natural response. Now if you talk about this type of response, this response is because of the voltage Vs which is applied in the network. So this is known as forced response. Okay, by the word you better understand why we call it as forced response, because some voltage is applied in the network and we're trying to get the response, and that's why it is referred as forced response. Okay, so please keep in mind, very important, this part is known as natural response, this part is known as forced response. Similarly, you can call it as first, second we'll see, this response is because of presence of no input, that's why it is also known as ZIR, or you can say it is a zero input response, and this response is because of some voltage, we call it as zero state response. Here there is no input, here there is some input, so depending upon the state of the network we will get a response. So this is known as ZSR. Okay, so your complete response is the sum of natural response and forced response. As I mentioned, this Vt, that is final response of a network, is mainly consist of your natural response or forced response, or you can say it is also consist of ZIR and ZSR. So this is two things. Now the next one is again I am rearranging this. So your Vt is basically given by Vt is equal to Va V0 minus Vas e to the power minus t by tau. If you see this and if you see this, these are the two terms. This term carry a time varying element and this term is a constant. So you can say that this is an steady state behavior. This you can say it is an steady state behavior. That means it does not depend upon the value of the time. At what instant the voltage is applied, or what is the solution of the network, you can say that the final value does not depend upon this value, and this you can say that it is a transient. So this you can say that it is a transient response. So yes, we have seen this is referred as steady state response of the network, and this you can refer as transient response. Why? Because this response vary with the time and this will remain as it is in the network. So we have seen all the three type of response, that is natural, force, ZIR, ZSR, steady state, as well as transient response. Okay, so just for your concept building, I have mentioned what are the three different type of response. However, you can go through your signals subject in which you will more study about all these three type of responses. Okay. Now finally, in the last, we'll see the most important aspects which is applicable in network while solving the problems that we'll try to understand. As I mentioned you that there are three time instant, and we have seen the two condition of switch. Either at t equal to 0 switch is open, or either at t equal to 0 switch is closed. So if it is open, so definitely at t equal to 0 plus also it is open. If it is closed, then definitely at t equal to 0 plus it is closed. If at t equal to 0 it is open, that means at t equal to 0 negative it is closed. If it is closed, that means it remains opened. So these are the very important conditions of a network while solving the initial conditions problem. Okay, so just keep in your mind, if t equal to 0, certain switch is open in the circuit, definitely at 0 plus instant it will remain open. But at when you talk about the past, actually t equal to 0 represent present. Okay, if you talk in terms of past, present and future, so in initial condition, this is the concept. At t equal to 0 your present state, and future, that means you are not predicting the future, but just for understanding, I am explaining you that whenever you are going for the positive instant of time at t equal to 0 to t equal to 0 plus, whatever the condition is remain here for the switch will remain here for t equal to 0 plus also. Similarly here also, and this is the condition. So this is past, present and future. So finally, if I talk about the capacitor, few conditions are arises. The conditions are, as I mentioned, t equal to 0 negative, t equal to 0, t equal to 0 positive, and t equal to, I say, infinite. Okay. Now friends, if you see, I mentioned earlier, the capacitor at t equal to 0 behaves like an open circuit. Why? Because at that instant capacitor will going to be charged. So whatever the voltage appears across that plate, it behaves like an open circuit. T equal to 0, the capacitor remains capacitor, and we generally find the solution. Now the very important condition comes to be at t equal to 0 plus. Now please see, t equal to 0 plus. T equal to 0 plus, two different situations comes across you, like either the capacitor is initially charged or capacitor is initially uncharged. So while we are considering these facts to solve the numerical problem, so if capacitor is charged, two conditions as I mentioned, capacitor charged and capacitor uncharged. So if your capacitor is charged initially, okay, I am talking about the initially. So if initially the capacitor is charged, so at t equal to 0 positive, it behaves like a voltage source. It behaves like a voltage source. Please keep in mind. It behaves like a voltage source. But if it is initially uncharged, that means at t equal to 0 negative, you find that the capacitor is initially uncharged, so that initial uncharged capacitor behaves like a short circuit. Okay, it behaves like a short circuit, and at t equal to infinity, whatever the condition at t equal to 0 negative will remain as it is. Okay, so from this point is very important. Similarly, we will see for inductor also, similarly we will for resistor, and we will draw one chart, and that chart is very important to solve all the problems of initial condition. So from here, once again I am explaining you, t equal to 0 negative, the capacitor behaves like an open circuit. At t equal to 0 it behaves like capacitor, that is we used to find the solutions. And t equal to 0 plus, there are two conditions exist, either the capacitor will be charged initially or either the capacitor will be uncharged initially. If the capacitor is charged, it starts behaving like voltage source at t equal to 0 positive, and it behaves like a short circuit at t equal to 0 positive if it is initially uncharged. And at t equal to infinite, the capacitor behaves like an open circuit. Now we will see, so this is our time instant, this is your t equal to infinite time. Okay, so just on the basis of this number line, or you can say t equal to 0 negative to t equal to infinite, we have just understand this concept. Now you know that I is equal to C dV by dt. Okay, little bit we will try to understand this concept. You know, yes, the capacitor is open circuit at t equal to 0 negative, but when you go at t equal to 0 positive, we are saying that the initially uncharged capacitors behaves like a short circuit. It means that this capacitor will be replaced by a short circuit. Short circuit means an infinite current is flowing. Ideally you can say an infinite current is flowing. Okay, ideally you can say an infinite current is flowing. So initially uncharged capacitor, it means at t equal to 0 positive, if you see this condition at t equal to 0 positive instant, if you see this I goes infinite, this I goes infinite. Okay, that means if the capacitor is initially uncharged, an infinite current will flow, and that's why the capacitor behaves like an infinite. However, that is ideally not possible. Okay, and only because of that I have mentioned you that V0 negative and V0 positive are equal. Very important thing. Why? Because the instantaneous change, or you can say abrupt change across the capacitor in terms of voltage is not possible, and that's why V0 negative and V0 positive is equal. But to solve those questions in problem, we have to apply this concept. So just keep in your mind, at t equal to 0 negative, capacitor behaves like an open circuit. At t equal to 0, it remains as a capacitor. To find the solution, at t equal to 0 positive, it is divided in two parts, either capacitor charged, either capacitor uncharged. If capacitor is charged, definitely behaves like a voltage source in the circuit, and if it is uncharged, it behaves like a short circuit in this manner. But when you talk about at t equal to infinite, again it starts behaving like an open circuit. Why? Because that capacitor will acting like again, why? Because the entire charge will be discharged. At t equal to infinite, we have already seen only the applied voltage will remain here. So under that condition, the capacitor starts behaving like an open source, that is open circuit. Okay, So this condition you must remember in your mind to solve the circuit that is RC based. Okay, so this is all about the capacitor. In my next video we will see about the analysis of inductor.